Hi, it's Mr. Green here, and I'm going to be taking you through the third lesson of our topic magnets and electromagnets. We're focusing on electron magnets today, but to start with, as always, a quick retrieval practice. There are 5 questions on the board. If you could pause the video while you attempt those 5 questions and unpause it when you'd like to go through the answers. So pause the video now. Okay, so question 1, what's a compass? So a compass is a bar magnet that can move freely that lines up with the Earth's magnetic field. Again, it lines up with the Earth's magnetic field lines pointing from north to south, and it can be used for navigation to see where you are and what direction you should be going in. Question 2, what is the test for a permanent magnet? Well, to test for a permanent magnet, you would use another magnet. Hold both poles of another magnet near it one at a time. If either of those poles repels the material, it is a magnet. If it doesn't repel, if it just attracts, it's just a magnetic material. And if it doesn't even attract it, it's not a magnetic material. Only a magnet can repel another magnet. What happens between two like poles? So if we put south next to south and north next to north, we get repulsion taking place. They push away from each other. Similarly, what happens between two unlike poles? If we put north next to south, we get attraction taking place. And question 5, what helps the Earth produce its own magnetic field? It's the molten metallic core constantly moving around, inducing a magnetic field around the Earth. So, today's learning objective is to know how to produce an electromagnet and how the strength of this field can vary around the magnet. So, just pause the video whilst you write that down as your title for today. Success criteria: describe how to show that a current creates a magnetic field, describe the direction of magnetic fields around wires and solenoids, and explain how the strength of a magnetic field can be changed. Okay, so if I get a wire and I place it through a piece of paper and I place 6 compasses around there, if I put a current through the wire, what would happen to those compasses? Before the current switched on, all those compasses would be pointing north. Now when I turn it on, this is what occurs. The compasses all line up with each other and appear to show the shape of a magnetic field. This tells us that when I put a current through a piece of wire, I induce a magnetic field around that wire. The shape of that magnetic field is circular, as we can see from these diagrams. So we get a circular magnetic field around that wire, getting weaker as it gets further away from the wire. What that diagram also shows you is something called the right-hand rule. If you hold your right hand in the position shown with your thumb up and your fingers curling around, the direction of your thumb is the same as the direction that the current's going in. So you can place the current up. The direction of your fingers shows the direction of the magnetic field. So you can see which way around it's going, which way it's going from north to south. So if you had your thumb up, then it would be going anti-clockwise. If you put your thumb down, it would be going clockwise. Now when we draw diagrams of this, you may get diagrams with current going up and current going down, but what they also like to show are the ones you can see on the left hand side, with the circle and the cross. What we need to know is if we can see a circle, the current is coming towards us. So use your right hand rule to put your thumb up, your fingers round, and point that towards you. You can see that those field lines are going in the same direction as your fingers on the left hand side. When it's a cross, that means the current's going away from you. So point your thumb away and you'll see those field lines lined up with the way it's going around. Imagine it's a dart. When you throw a dart away from you, you can see the cross. So that's travelling away. When you see a cross, the current's travelling away from you. If you throw a dart towards someone, you'll see a point. So when it's a point or a single circle, that's coming towards you. Okay, with that in mind, use the right hand rule to sketch the diagrams below and show the direction of the compass needles for each piece of wire. So this is the current coming out towards you on the left hand side, current going in away from you on the right hand side. Pause the video whilst you do that diagram. Okay, so for the left hand side with the current out, your arrow should look like this. So the current coming towards you, your fingers curling around, showing you the direction of that field. When the current's going into the piece of paper, it should look like this. Again, the opposite direction. The current's going in the opposite way, so the arrows go the opposite way around. Again, pause the video and ensure you've got those copied down accurately. Okay, look at these two diagrams here. We've got two questions. In A, why are the compasses all aligned in the same direction? And in B, which direction is the current flowing in the left and right hand side of the wire? Pause the video while you attempt that and restart to get the answer. So, in A, why are they all pointing in the same direction? Well, they're compasses. They should be lining up with the magnetic field of the Earth as long as there's no other magnetic field near. They're all surrounding a wire there, but they're all pointing to magnetic north. That means there's no current going through the wire, so they're following the Earth's magnetic field. In B, we can see the direction that each compass is going in there. So use our right hand rule. On the left hand side, the one that's furthest up on there, we can see it's going around in an anti-clockwise direction. That means the current's travelling up that wire. On the lower part of it, on the right hand side, we can see that the compasses are going the opposite way, so it's going down on there. So our key point, a current carrying wire is surrounded by a circular magnetic field. And we can see reversing the direction of the current reverses the direction of the field. Now we're going to move on to solenoids. What is a solenoid? Well, a solenoid is a coil of wire with an electric current running through it. So instead of having our straight piece of wire like we've previously had, we now coil that wire up and wire it round almost like a spring. Now, will coiling that wire affect the shape of the magnetic field induced in it? It will do. It will make it look like the shape around a bar magnet. A solenoid produces a much stronger magnetic field than a single wire. And when we coil it around, we see those field lines are going in the same direction as they would for a bar magnet, with north coming out one side, south around the other. So by coiling it up, we've made a more regular magnet than we can see. Again, the diagrams above and below show when we have a solenoid, that bar magnet is exactly the same as the one below it. The solenoid just turns the magnetic field from being circular around the wire into a more regular bar magnet. So what's the strength of that magnetic field depend upon? It depends on three things. Number one, it depends on the amount of current in the wire. The more current we have in the wire, the stronger the field is. It depends on the number of loops in the wire. The more loops we have, the stronger the field is. And it depends on how far away you are from the wire. The closer you are to the wire, the stronger the current is. Now, solenoids, magnetic field is strong and uniform, it has the same strength and direction, but we can increase that even further by putting a block of iron in the centre of the coil. That iron core becomes magnetic itself whenever the current's flowing. The magnetic field of the core and the coil combine, making a stronger magnet overall. This makes an electron magnet. Placing a metal in the centre of a solenoid makes it into an electron magnet. This has got a much stronger field than a solenoid and can be switched on and off. Again, we can affect the strength of this electron magnet by changing the number of turns on that coil. More turns, stronger magnet. The size of the current itself, the higher the current, the stronger the magnet. And we can change the material we place in the core. We can place iron in there for very strong. If we place steel in there, it's not quite as strong. Cobalt and nickel in there will also affect it. So depending on the material in the core, that will change the strength of the magnet. But your general rule is the number of turns is high, the strength of the magnet is high. The size of the current is high, the strength of the magnet is high. Okay, have a quick look at this one. So put the following in order of their magnetic strength. You've got electron magnets and MRI scanners, a very strong permanent magnet, strength of the field 1 centimetre away from a wire carrying 5 amps, and the strength of the Earth's magnetic field. Which do you think is the strongest? Which is the weakest? Place them in order. Pause the video while you do so. Okay, they go in this order. The strongest are the electron magnets used in MRI scanners. They're 10 Teslas. We measure the strength of a field in Teslas. Slightly weaker than that is a very strong permanent magnet. 10 times weaker, a very strong permanent magnet. 10 times weaker than that is the strength of the field 1 centimetre from a wire carrying 5 amps. And the weakest of them all is the strength of the Earth's magnetic field, 0.01 milliteslas. That's really, really, really weak. But again, it has enough of an influence to push those compasses in the right direction. How can we use electron magnets? So electron magnets can be used to attract and pick up things that are made from magnetic materials like iron and steel. You'll have seen electron magnets used in scrapyards. Now if we used an ordinary magnet, we'd be able to pick up the scrap metal, but then we wouldn't be able to let it go. So using an electron magnet means the magnet can be switched on when we want to pick up stuff and then switched off when we want to drop stuff off. Okay, there's a few questions here for us, 5 questions. It's a recall on what we've just done. If you could pause the video and answer all 5 questions for me, I'll come up with the answers after you've unpaused. Okay? Okay, question 1. In the right-hand thumb rule, what does your thumb represent and what do your fingers represent? In the right-hand thumb rule, your thumb represents the current and your fingers represent the magnetic field. Question 2. The magnetic field of a solenoid. It is the same as the bar magnet. All the lines inside the coil should be straight and parallel, but on the outside it is just the same as a bar magnet. Again, please pause the video in between these to make sure you've got the answers right. Question 3. How can we increase the strength of a magnetic field produced by a solenoid? Okay, so in a solenoid we can do the strength of the solenoid will increase by placing an iron core inside the coil. We could increase the current in the coil, and we could also increase the number of turns around that coil. Question 4. What's an electron magnet and how does it work? An electron magnet is a magnet whose field can be turned on and off with an electric current. The most common form is a coil of wire around an iron core. When the current flows through the coil of wire, a magnetic field is formed, or you can say induced for more marks, around the wire and the core is magnetised. Finally, one use of an electron magnet, just been through it, that is in scrapyard cranes for picking up and moving scrap metal. There are lots of other ways we can use it. Things like relays will use them. Okay, so a quick application question. So using what you've known, a current carrying wire, which is shown by the red dot, produces a following magnetic field pattern when viewed from above. What direction is the current flowing in? So forget what shape that dot is in the middle, use your right hand thumb rule to work out what direction the current's flowing in, and in what direction would the field lines point if the current began flowing in the opposite direction. Pause the video whilst you attempt that question. Okay, so question 1a, the direction the current's flowing in, it's flowing away from us, it's flowing into the screen. We can see that from the shape of the field lines. The field lines are going anti-clockwise. If we change our thumb, we can only get it pointing in that direction if it's pointing towards the screen with our right hand rule. Question B, in what direction would the field lines point if the current began flowing in the opposite direction? Field lines would point anti-clockwise if the current were reversed. If we reverse the current, we reverse the direction of the field lines. Okay, I've supplied exam questions for you, which are on electromagnetism. If you could attempt those towards the end of the lesson, and again, double check I've given the mark scheme to the member of staff there. Okay, speak to you soon. Hope you have a good one, and I hope you found that useful. Goodbye.